How's everybody doing? Feeling okay? Feeling like we have another week of torture and then it's all over? It's all coming to a big conclusion rather quickly. Let's take a look at this picture of the soap bubbles. Can you guys see that on the monitor over there? Is there a soap bubble picture up there? Okay. So this is something that we started talking about yesterday, this idea that we have interference in thin films. Okay, and the basic concept is really not that hard to understand. The idea is this: if your film has some thickness to it, there's going to be a reflection off the front surface and a reflection off the back surface. That's essentially the whole idea, okay? Reflection off the front surface, reflection off the back surface. But the way those things add up out here, we have to be a little bit careful about, because these electromagnetic fields or electromagnetic waves are just that. They're waves, okay? They behave sinusoidally. And when you add up the electric field out here, you have to take into account, is that electric field pointing up at that moment in time and space, or is it pointing down? And if one of those reflections was pointing up, the other one was pointing down, you would get zero reflection. And so that's what we developed yesterday, was an equation for anti-reflection coatings. What does the thickness have to be? And what we said was T equals M lambda in that film divided by 2. This is for destructive interference in the reflection. Okay, so we talked about this yesterday. This is like the coating on your glasses. That anti-reflection coating that you put on your glasses has a thickness that is governed by this. Remember, M is an integer, right? M is 1 or 2 or 10 or 20. And so when the engineers design the thickness on your glasses, they pick a certain M, they calculate lambda film, and this equation then tells you what thickness you have to have. But if we shift that film by just a little bit in thickness, all of a sudden it will go from destructive interference to constructive interference. And let's look at the opposite case, which is a high reflection coating. Okay, and for that high reflection coating, the thickness.
Mark, you're writing over the superimposed image.
Okay, you can take it off for a second, and we'll put it back in just a minute. Okay, the thickness T for the high reflection coating is the following. T equals M minus 1/2 times lambda film all over 2. Okay, and we've shifted the reflection by a half a wavelength. And when we do that, now it becomes constructive interference. And this you might want on your specialized mirrors. Okay, so if you're designing a laser mirror and you want as much laser power to come off the mirror as you can get, then you put a coating on it that has this particular thickness. All right. Anybody have anti-reflection coatings on your glasses? Anybody have those? Okay. What happens with those coatings? What's very annoying about those coatings? What do you notice with your glasses?
Well, the light doesn't bother me. So
Okay. The glare doesn't bother you. That's good, right? That's what they're designed for. But you might notice that they get dirty very easily. And particularly if you take your finger and touch the glasses with your finger, all of a sudden that fingerprint is really visible. Why is that visible? Because you have a film here. When you touch it with your finger, you're putting a little bit of oil from your finger onto the film. And so you are changing the thickness of the film. And if you change it by just the right amount, it will go from destructive interference to constructive interference. And all of a sudden that fingerprint shows up extremely well. Okay? And so that's the downside with anti-reflection coatings. You have to keep them clean. Because if you just change that thickness by a half a wavelength, all of a sudden it turns into a high reflector. Okay. Joe, why don't you put that picture back up for a second? So the picture that you're looking at is a picture of soap bubbles, okay? And the one on the left is a full bubble, and the one in the center is just a bubble film, okay? It's a thin film. So let's take a look at that center picture, and what do we see? Here is the film. Okay, film just means a thin layer of water with soap in it. And now, if you look at that picture carefully, what you see is stripes. Okay, and the very top, it's going to be maybe blue, then green, then red, and then it'll go back to blue, and green, and red, and so on down. We just picked 3 of the colors in the rainbow. But if you look at the very top of that picture, there's no light there. It's black. Okay, this is the front view of that soap film. But let's think about it looking at it from edge on. What does that soap film actually look like? What it looks like is this. Okay, it's very thin at the top and very thick at the bottom. That's what that soap film is doing. Why is it doing that? Because gravity is acting on it. Gravity is pulling it down. The rim, the wand of the soap bubble device is trying to hold it up, but gravity is pulling it down. And so it gets thicker at the bottom, it's thinner at the top, and eventually gravity is going to win and the soap bubble pops and disappears. Okay, so if I think about light coming in here, and we have all the colors of the spectrum, sunlight, then what reflects off that first very top part is nothing. Okay, nothing reflects off the top of the soap bubble. And that's because there's a phase shift between the first reflection and the second reflection. And that phase shift means they exactly cancel out. Where the soap is really thin, you can ignore the propagation through the film, and so it's that phase change of 180 degrees between the front and back reflection that means no light returns. And so that's why that soap bubble looks black. Okay? All the light just keeps going right on through. The transmission is 100%. Okay, but as we go down the soap bubble, all of a sudden we start to see these colors. And for instance, when we get down to here, the reflection is blue. And that's because blue has a nice short wavelength. And so it can match up to that thickness just right to give us a high reflection for blue. But the red wavelengths are longer, and so they don't match up at that thickness. They keep going on through. But if we keep going down, the next one is green. And that's because green is a little bit longer, and so it needs a little bit thicker film to have a high reflection. And if you keep going down further, then you get to red, because red is even longer. And so the arrangement of these colors is such that the thickness determines which ones get reflected well. Okay? So you see that in that center picture, right? The top is black, and then we go down, and then you go through the various colors as you propagate down through the soap bubble. And the last picture on the right is this same idea, except it's oil on pavement. And it's really the same idea as this. The different thicknesses of the oil are going to reflect different colors primarily. The oil happens to be a little bit thicker in the center than it is on the edge, and so you get this rainbow that sort of goes out radially. Okay, let's try an example of one of these problems. Joe, you can take that picture off. Thank you. Okay, let's do the following. We're going to take a soap film, and we will use a laser that has a wavelength of 691 nanometers. And we're going to say that the film is soap and water, so the index of refraction is very close to that of water, 1.33. And here is our soap film, and it has a thickness T. And now let's calculate what thickness T do we get maximum reflection. So here comes our laser, and we want to get maximum reflection. And let's ask the question, what T do we need to use to get maximum reflection? Okay, so we go back to our equation for maximum reflection. That's the constructive interference case. And what we wrote down was thickness T was m minus a half times lambda in the film, and then we have to divide by 2. Okay, the reason you're dividing by 2 is because it's double pass. Light has to go through the film, reflect, and come back. Okay? So, we know what lambda film is. Lambda film is lambda naught divided by n. Okay? And now we can pick any order we want. M is just an integer. We can pick 1, 2, or 3, okay, or 4, or 10, or 20, but let's just do 1, 2, and 3. So the thickness is going to be what? Well, let's do m equals 1. So I have 1 minus a half, lambda naught over n, and I'll just slip that 2 up to there. The next one is 2 minus a half times lambda naught over 2n. And the third one is 3 minus a half times lambda naught over 2n. That's our lambda naught. That's our n. We have all the other numbers here, and so we can calculate those, and you can double check my numbers if you like. But I got the following: 129.9 nanometers, 389.7 nanometers, 649.4 nanometers. Those are typical numbers that you might see in a real coating on your glasses or on your mirrors. And now you see the difficulty in making those coatings, right? 650 nanometers, that is pretty small, okay? The human hair is something like 50 to 100 microns, where a micron is 1,000 nanometers. So you're talking about something much, much smaller than the thickness of a human hair. You have to be able to put that coating on just that, very specifically. Ignore that man behind the curtain. Okay, let's talk a little bit more about this idea of diffraction, and specifically, let's revisit this idea of Huygens principle. Okay, so we didn't really talk too much about Huygens principle the other day, but it's not that hard to understand, and it leads to a nice discussion about diffraction. So Huygens principle is the following. A wave is made up of spherical wavelets. Okay? A wave is actually made up of these things, these spherical wavelets. What does that mean? If I think about a plane wave, then these are the phase fronts that are moving along, right? My distant star is sending me some starlight. The light that reaches me is essentially a plane wave, okay? It has no X or Y dependence. But Huygens principle says that every part of that wave is actually made up of spherical wavelets. It's like you took a whole row of pebbles and dropped it in the pond at the same time. Each one emits a spherical wavelet, and the way the wave adds up depends on all those spherical wavelets. You have to add up the fields from all of them to get the resultant wave. Okay? So if you go far enough away here, those waves spread out and you recover your plane wave. Let's see how this works when we're dealing with a small hole that the wave goes through. Okay, this was our single-slit problem that we talked about yesterday. Here comes our plane wave. And if every part of that plane wave is really made up of little spherical wavelet oscillators that are going to spit out these wavelets, then by putting it through this little hole, I'm really just going to isolate a couple of those. And both of those are going to emit spherical wavelets. And so now if I look at a distant screen, I see light spread out all over the place. Okay? Not only does it spread out all over the place, but there is some interference between the two because they're not in the same location. One of those little guys is on the top edge of the slit, the other one's on the bottom edge of the slit. And so the wave spreads out, but we also in fact get interference at the screen. And so if I think about what sort of interference pattern I'm going to see, and we'll draw it like we did yesterday, with the intensity of the light to the right being big, then I in fact see the following picture. I see a bright spot in the center, but then I see little ripples going out to either side. Okay, that bright spot in the center aligns with the hole. The ripples are due to the finite size of this hole. And in fact, this dark fringe right here, there is no light there. Okay, it's dark. Same up there. This one is, of course, a bright fringe. All right, anytime you send light through any hole, it does this. It spreads out and it gives you an interference pattern that looks like this. Okay. Let's see if we can figure out where those dark fringes are located. All right, to do that, we need to redraw this slightly. Let's make it a little bit bigger. And let's say that the full width is W. Okay. Let's just worry about light from the top and light from the center. And now when we go to our distant screen, we're worried about this angle theta that we talked about before. It turns out that using this sort of picture, you want the light from this position to be a half wavelength out of phase with the light from this position. And so the dark fringes are in fact located at the following position. W sine theta is equal to m lambda, where again m is an integer. Okay, width W, angle theta, wavelength, and an integer number. All right, but this is kind of interesting because what we're saying is light that goes through any hole spreads out like this. And this is really what happens, right? Happens in the lab, but it happens out in nature as well. All right, let's try an example, and let's do the following. Let's say that we're going to shine light through a slit. We will let the light have a wavelength of 480 nanometers. Let's use a slit W of 20 microns, so that's 2 times 10 to the minus 5 meters. And we're going to say that the screen distance L is 0.5 meters away. And let's ask the question, what is the width of the second bright fringe? All right, so we're going to have to think about this one a little bit. And I think initially what we should do is probably draw a picture. Okay, so we have a plane wave coming in. It's got wavelength lambda. It's going to hit a slit of width W. It's going to go a distance L to a screen, and then it's going to leave a pattern on that screen. And the pattern, we know what it looks like. It's this. Now what they want is they want the width of the second bright fringe. That's the second bright fringe. Let's call that H, and that's what they want to figure out. All right. I think we need some coordinates here. So this is the horizontal axis. If we go to the first dark fringe, that's angle theta 1. If we go to the second dark fringe, that is angle theta 2. And let's label this as y1 and this whole height as y2. Okay, y1 is going up to the first dark fringe, y2 is going up to the second dark fringe. And now we need to figure out how to calculate h. All right, h is of course just going to be the difference between y2 and y1. All right, that's not too bad. But y2 looks like I can put it in terms of this triangle. I have the angle theta and I have the distance L. So y2 is going to be L tangent of theta 2. y1 is going to be L tangent of theta 1. All right. I get a common L there, so I can factor it out. Tangent of theta 2 minus tangent of theta 1. And now we do what's called the small angle approximation. And we talked about this before. We use it a lot in physics to simplify these problems. And what it means is, before we said, oh, sine theta is approximately theta, if theta is in radians. That's the small angle approximation. But that's the same as saying that sine of theta is the same as tangent of theta. So this whole thing simplifies to L sine theta 2 minus sine theta 1. And now we know where those things are located, because we have an equation for where the dark fringes are located. And what does it become? It becomes the following. We get L, and then we have 2 lambda over W for sine theta 2 minus 1 lambda over W for sine theta 1. Okay, and now we have all those numbers and we can plug it in and try it. So we get H is equal to L, which we said is 0.5 meters. We have 2 times lambda, which was 480 nanometers. Nano is 10 to the minus 9. We have to divide by W, which we said was 2 times 10 to the minus 5 meters. And then we're going to subtract 1 lambda over W. Okay, so somebody punch this into your calculator and I will approximate it here. This is 0.5. We can factor out the wavelength, so we have 480 times 10 to the minus 9. And then 2 minus 1 is obviously just 1, and so we can divide this whole thing by 2 times 10 to the minus 5. Bless you. All right, so somebody help me approximate this. Let's see what we get. So 0.5 over 2, well, 0.5 is a half. Divide by 2, we get a quarter. So we're going to get a quarter of 480. And then we've got a 10 to the minus 9. And we're going to take this 10 to the minus 5 and put it up on top. So we're going to add 5 up there. And so we get a 10 to the minus 4. A quarter of 480, that's not too bad, right? That's got to be 120 times 10 to the minus 4. So I'm going to say that h is 120 times 10 to the minus 4 meters. Somebody get that as an answer? Which is the same as 1.2 centimeters. If you get something different, just let me know. I think we did that correctly. So the height here, h, of that fringe is first dark spot to second dark spot, and that corresponds to 1.2 centimeters. So this is maybe something that you've done in the lab, right? You take a laser, you shine it through a small hole, right? It's got to be pretty small. This is 20 micron hole. And you can see this pattern spread out on a screen that is a ½ meter away. Measuring something that's 1.2 centimeters is nearly trivial, right? You can hold up a ruler and just mark those positions. And so not only is this a way to determine the wavelength of the light, right? If I have this number, I can backtrack and determine the wavelength of the light, but it's also a way that I could determine the size of this hole if I knew the wavelength of the light. Okay, so even though the hole is only 20 microns in size, just by measuring this pattern over here, you can in fact infer how big that hole is, which is kind of cool, right? You need to do this in a lot of physics and engineering problems. How big are the holes in this substrate? Okay, did anybody else get that answer? Is that right?
Yeah.
Okay, good. Any questions about this one? Okay, this is very similar to some of your homework problems. Okay, why do you care about this stuff? Let me tell you why you should care about this stuff. It relates to something called resolving power. Okay? Resolving power means the ability to resolve two different objects. So let's say we have the following. Let's say we have two light bulbs. Number 1, number 2. And we're going to put a slit right there. There is light coming from these light bulbs towards the slit. And when it goes through the slit, let's image it onto a distant screen. There is light coming out from light bulb 1, light coming out from light bulb 2, and we know what those patterns look like. Light bulb 1 looks like that. But light bulb 2 could in fact overlap with that one just a little bit. Okay, and we get two of those patterns. Those are called sync patterns. And they are in fact hard to distinguish the two spots. Okay. It's very hard to distinguish that spot from that spot if they are overlapping. So, how do we calculate the minimum resolvable angle we do it like this. Let's just take a light source, a light source. It's coming into our slit. These are our lights. And this angle here, we want to figure out what is the minimum that we can see. And we will call the diameter of the slit d. Well, it turns out that the minimum resolvable angle, theta min, is the following: 1.22 lambda over d. So let's go back to the question. Why do you guys care about this stuff? Okay. When you're driving down the freeway and you see a car coming the other way and they're very far away, what do you see? Do you see two headlights or do you see one headlight? You see one headlight when they're very far away. It just looks like one light source. And that's because those two light bulbs are so far away that you are under theta minimum. The two diffraction patterns overlap on your eyes, and so you can't tell if it's a motorcycle or a car. As it gets closer, theta starts to increase. And eventually it gets to this value right here, theta min, and now you can resolve it. And you say, oh, that's a car. That's not a motorcycle. Okay, so let's talk about the different parameters in here that go into that. One is the wavelength of the light. Okay, what colors are coming from the light bulbs. But the other thing is D right here. What is D? D is the diameter of the hole that the light goes through. But if you're looking at it with your eyeballs, what is D? What does that refer to? Anybody know? D is the diameter of your pupils in your eye. Your pupil is the slit. The screen is, of course, the back of your eyeball, which is the retina. But the pupil is D. And so if your pupils are closed down, if D is a small number, then theta min goes up. That car has to get much closer to you before you can distinguish that it's two headlights and not one headlight. But if your pupils are wide open, then D is bigger, theta min is smaller, and now you can distinguish it as two headlights much further away. And you might have already experienced this, okay? One, maybe driving around at night, but two, when you have some text on a piece of paper and you're sitting in a dark room and you're trying to read the text, it's very hard, especially when you get older or ancient like me, okay? It's really hard to read that text in a dark room. Why? Well, because your pupil opens up and you get all these spherical aberrations in your eye and so forth, okay? And so there's not only this going on in terms of your resolving power, but there's the shape of your eyeball, there's the spherical aberration, there's all sorts of other things going on. But what about this lambda, okay? Lambda is the wavelength of the light going in. And this means that smaller lambda goes to smaller theta min or smaller focal spot. It turns out that if you're trying to focus a laser beam down to a very small spot, you can do it, and the limitations are similar to this equation, and the smaller focal spot will arise from using a smaller wavelength. And this is also something that you're kind of familiar with, right? Because when you have a DVD disc, right? Here is a CD or DVD. Your DVD player has a laser in it, and it is using a particular wavelength of laser light. It's up in the red region of the spectrum. But if you want to put more data on your disc, you need to get a smaller focal spot, which means you need to lower the wavelength. So does anybody have one of these fancy new DVD players that plays HD DVDs? What is it called?
Blu-ray.
Blu-ray. Why is it called Blu-ray?
Because
Because it
it has a smaller wavelength.
has a blue laser in there instead of a red laser. It spits out a blue ray. Okay? And that blue ray has a shorter wavelength than red, and so you can get to a smaller focal spot than red, which means you can put more data on the disc. In fact, you can put a full high-definition movie on the disc. All right, let's take a 5-minute break, and I will see you guys back here in just a few. Hi guys, welcome back. Let's take a look at one of your homework problems, and this is a single-slit diffraction problem. Okay, and let's just review for a second what our equation was for the single-slit diffraction. What we said was the dark fringes are located at a specific position determined by that. W sine theta equals m lambda. W is the slit width. Okay, and I think in your book they use D, but it's the same thing. This is the angle to the dark fringe. M is, of course, an integer, and this is the incident wavelength. Okay, so like we said before, if we have light of wavelength lambda coming in, it hits a hole of width W. It's going to make a pattern on a distant screen, and that pattern has this characteristic shape. So in this problem, it says the following. It says monochromatic light falls on a slit that is 2.2 times 10 to the minus 3 millimeters wide. Okay, so what they give us is W, and they say, for my numbers, it's 2.2 times 10 to the minus 3 millimeters wide, which in meters would be 2.2 times 10 to the minus 6 meters. It says, if the angle between the first dark fringes on either side of the central maximum is 28 degrees, dark fringe to dark fringe, what is the wavelength of the light used? So what they're saying is this. That angle right there is 28 degrees. Okay? But in our equation, the angle to the dark fringe is always relative to the horizontal. So that angle right there has to be half of it, 14 degrees. All right. I think we can probably plug into this equation now and calculate the wavelength of the light used. So let's take a look. W sine theta equals m lambda. If we're talking about the first dark fringe, then we're using theta 1, and in that case, m is 1. Right? This is plus 1. This is plus 2. Down here it would be m equals minus 1, m equals minus 2, and so forth. All right, it looks like we have enough that we can calculate lambda. Lambda is just w sine theta 1, and now we have all those numbers. W is 2.2 times 10 to the minus 6 meters. Theta 1 is 14 degrees. We're going to take the sine of 14 degrees. Somebody punch that into your calculator and tell me what you get, and we'll see if I can earn some homework points. Okay. 5.32 times 10 to the negative 7, and that is meters. That's what I got here on Wolfram Alpha. Let's plug it in and see. 5.32, okay, which is the same as 532 nanometers. So let's try 532 nanometers and see if it'll take that as our answer. And the units are going to be nm, nanometers. And it says correct. We got it right. Okay, you will have different numbers, of course, for your angle and probably for your slit width, but you should get something in that range, okay, somewhere in the visible spectrum. Okay, any questions about this one? Okay. So let's talk a little bit about diffraction gratings. And diffraction gratings are essentially the following. We're going to use many, many slits in our piece of cardboard or whatever it is. Okay, so this is many different slits, and we're going to come in with a plane wave. So, how do we analyze what's going to happen? Well, if we go back to Huygen's wavelet idea, what this means is that each one of these is going to emit spherical wavelets. And all those spherical wavelets are propagating outward, and they're going to go to a distant screen. So any point on the screen here is going to be a combination of the fields from 1 and 2 and 3 and 4 and so on, all the way down. Okay? But the one from 2, if I'm looking up here, it had to go a little bit further than the one from 3, than the one from 4. Each time you go down, they have to go a little bit further to the screen if I'm looking at the top of the screen. Well, it turns out that all these things are going to add up and make a pattern that looks like this. You've got these bright spots, and then you have little small fringes in between. Okay. The location of these bright spots is determined by the wavelength coming in and the spacing of the holes. Okay? And those bright fringes are going to appear at the following locations. D sine theta is equal to m lambda. Okay. What is sine theta? Well, again, if you take the center of this whole thing, theta is going to be relative to that center line. So this would be theta 1. That would be theta 2. This would be theta for negative 1, for negative 2. Okay, so all these different spots here correspond to m equals 0, m equals 1, m equals 2, m equals minus 1, m equals minus 2, and so on. Okay. So diffraction gratings we use, of course, all the time in physics, but in fact you can see them everywhere. Okay? So if you go back to your compact disc, the compact disc has a whole bunch of little spots on it. And those little spots act just like these little holes. Okay? Spherical wavelets are going to come off of each of these little spots. And if you guys look at this, you might be able to see a whole bunch of different colors coming off of that. If you can't, let me turn on my handy dandy flashlight app, which everybody should have on their phone now, right? It's a great thing. I still got to post that picture of you guys in class. But let's see if we can see on the camera. Tell me, can you see a rainbow coming off that thing? Okay. All right. So some angles are going to work just fine, and I'll just move it around a little bit so everybody can see it. Okay, this is a white light LED, so it's spitting out all these different colors. And now as I rotate this CD, you should be able to see a rainbow of colors. Why is that? Because every color that comes in is going to have a different wavelength, and if it has a different wavelength, then it corresponds to a different theta. Everything else is the same. D is the same, M is the same, so different wavelength means different theta. They're going to spread out in all these different directions. Now compact discs, excuse me, we'll edit that out, right? I had this physics teacher one time, and he was talking about like resistance in circuits, right? And he starts drawing this big circuit, and he goes, yeah, you got your capacitors over here, you got your inductors over here, and then you got your sheep. And he stops and he goes, sheep. And he's trying to figure out where that came from. Sheep. Yeah. All right, Joe, hit the rewind, edit that out. Okay, so compact discs also work using interference, which is kind of interesting. Okay, compact discs actually use destructive interference. Okay, how does that work? Well, we know what the compact disc looks like. It's got a hole in the center, and then there's a whole bunch of spots on it. Okay, so this is sort of the top view of our compact disc. And if I think about the side view, what those little spots are actually little plateaus. Okay? And the way this works is the following. There is a laser that comes in. And the laser hits half of the spot and half of the disc next to that little spot. The light that comes back off goes to a detector. This is our detector. Okay. if this thickness, T, is just right, if that thickness T is lambda over 4, then double pass means lambda over 2. Then the two reflected beams are 180-degree phase shifted. Okay, and then you get no reflection. If there's no little plateau there, then you get full reflection. And so that's how you make your zeros and ones on your little disk, is you have these little plateaus and these little pits in there that change the reflection. Okay, the whole disk is spinning around really rapidly. The laser head, there's a lens in there, of course. The laser head reads those little bits as it goes by, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0. That's your binary data stream. The detector sends it to the digital to analog converter, which turns it back into music. Okay? So all those little patterns that you see on there that you can actually see when you do that rainbow trick that we just checked out, that corresponds to those little features that are on the CD. Okay, let's talk a little bit about rainbows. Okay, rainbows are kind of a fun topic of conversation because you've all seen a rainbow out there. Probably some of you have seen the double rainbow. It's glorious, right? It's like one of my kids' favorite videos is the double rainbow. How do rainbows work? Rainbows work because of something called dispersion. So, remember when we were talking about the index of refraction, right? The index of refraction, n, came into the speed of the wave. V is c over n. But n is not just some fixed number. It actually depends on wavelength. Okay? The index of refraction depends on the wavelength that you're talking about. So when I go from air into glass, and let's say that I'm using sunlight. Here's my sunlight. When it goes into the glass, we know what happens, right? It refracts, and so it's going to bend at a different angle. But it bends this direction if it is red. It bends to this direction if it is green. And it bends to this direction if it is blue. This is because the index of refraction of glass depends on the wavelength. Okay? N for red is, for this particular glass that we're talking about, 1.520. The index for green is 1.526. The index for blue is 1.531. Okay. Most glasses have a higher index when you go to shorter wavelengths. So the blue is a shorter wavelength. It has a higher index than the red. Now, we didn't draw this to scale, okay? Those things aren't going to be spread out nearly that much because these numbers are pretty close to being equal. We just did this for simplicity here. So you're all familiar with this because you've all listened to Pink Floyd at some point in your life, and you probably have seen the Pink Floyd album cover, right, that has the t-shirt on it, and they're sending in white light into this prism. Okay, and what happens is the different colors spread out, and coming out the other side of the prism, you get 3 different beams, and the top one is red, the middle one is green, and the bottom one is blue. And it's the same idea that we talked about here. Okay, light goes into the glass, sees a different index for those different colors. If it sees a different index, then Snell's law tells us that the incident times sine of the incident angle is equal to the transmitted times the sine of the transmitted angle. These things are the NT. And so by changing NT, you're going to change theta T. Now, if you look at the Pink Floyd album cover, you'll see this picture on one side. And if you flip it over, they have this picture again, but those things are reversed. Blue is on the top, green is in the middle, and red is on the bottom. So it's kind of cool. Like one of the ways it's correct, and then you flip it over, and it's incorrect. All right? And the reason it's incorrect is that most glasses behave the exact same. For almost all different types of glass in the optical region, the visible portion of the spectrum, we've got an N that decreases with wavelength. Okay, long wavelength is red, short wavelength is blue. And so blue has a higher index than red, and that means that blue bends more when it goes into glass than red. Okay, and this whole thing is called dispersion. So, how do we understand rainbows with this picture? So rainbows arise from dispersion. Okay, let's draw a picture of this thing. Here's the sun. Here's a cloud. And it is raining. So there's these droplets of water coming down. Okay, sunlight is going to bounce off these things and come back to you, and you're going to observe the rainbow. First question. Here's the Earth. Where are you in this picture? You're standing on the Earth somewhere. Are you directly under the cloud? Are you over here to the right of the cloud? Or are you over here to the left of the cloud? Where are you standing when you observe the rainbow? Anybody know? You are right here. Okay. If you're over here, you don't see a rainbow. If you're right under the cloud, you don't see the rainbow. Anytime you see a rainbow, the sun is going to be behind you. Always. So try that next time you see a rainbow. Look at the rainbow, turn around, right behind you. That's where the sun is. Okay? And this is why you can never get to the rainbow, right? Because you get closer and the rainbow moves further away from you. It's very annoying. So what happens? Here comes the sunlight. It's going into these water droplets, right? This is, of course, water. Something happens, and all these different colors start to spread out, and you see the rainbow when you look up, okay? Let's see if we can figure out what is happening in those water droplets. So we're going to do what physicists always do, assume a spherical water droplet, okay? And now sunlight is coming in. Sunlight, of course, has all the colors. One of those colors is red, okay? And so let's map out where red goes. When red comes into the water droplet, it bends a little bit. Okay. It hits the back, it comes down, and now it bends again on the way out. This is our red ray of sunshine. But blue is also in the water droplet, and when the blue comes in, it's going to bend a little bit more. Okay, so it's going to bend down further in the water droplet. It hits the back of the water droplet at a lower point than the red, and so it's going to bounce back a little bit more horizontal. And so it comes out right here. This is how the color separation works in a water droplet. The different index of refraction, which depends on the wavelength, tells you that the red is going to bend a little bit less than the blue, and with the bounce off the back of the raindrop, the end result is the blue comes out at a little bit higher angle than the red, okay? So when you look up in the sky and you see a rainbow, what this means is you have to look at a higher angle to see the red, a lower angle to see the blue. And so when you look at a rainbow, red is on the top and blue is on the bottom. Okay? And you can convince yourself pretty quickly of that based on this geometry. But if you see a double rainbow, which is really cool, right? Anybody seen a double rainbow other than in that video? Okay. Single rainbow will be red, and then green, and then blue. But a double rainbow, there is a dark band, and that dark band in between them is actually called Alexander's dark band. And then if you keep looking up in the sky, and conditions are just right, you'll see a second rainbow up here. Okay, and that second rainbow, in fact, is inverted, red to green to blue. Okay, it's dark in between, and then it's inverted. So, if the first rainbow comes about from this phenomenon, what do you think creates the second rainbow? What happens in the water droplet to create the second rainbow up there? Anybody know? It turns out it bounces twice in the water droplet, okay? And in fact, it goes the other way. It goes around this way, bounces twice, and that creates this inversion of the second rainbow. It also means the second rainbow is a lot dimmer than the first rainbow. First rainbow is pretty bright because you have one bounce. A lot of that light comes off. Second rainbow, there's 2 bounces in the water droplet, and so a lot of the light is lost. So it's usually really hard to see a second rainbow just for that reason. It's much dimmer than the first rainbow. Okay, any questions about rainbows? Go out and look. They're cool. And see if you can see this Alexander's dark band. It's really interesting. All right, let's talk a little bit about one of the most famous physics experiments ever. And this was using something called a Michelson interferometer. Okay, and the particular experiment that I'm talking about is called the Michelson-Morley experiment. So, what do interferometers do? Well, let's look at the name. There's interference in the name, and that's exactly what they do. Interferometers will take an E1 and they will add it to an E2 to get some resultant field. And when I add E1 and E2, there's a couple different things that can happen. They could add up constructively. And we saw last time that if you add them up constructively, it gets bigger. But they could add up partially constructively. And partially destructively. Or it could be completely destructive. What an interferometer does is it moves E2 back and forth ever so slightly. And when it moves E2 back and forth, you go from the condition of constructive to partially constructive to destructive. Okay? And what you're going to monitor is E3. Okay, so this is the basic idea with an interferometer. Take 2 fields, move one of them back and forth slightly, and now you can measure the output. All right, so let's talk about this idea of the Michelson interferometer and what it actually looks like. So typically you will use a laser in a Michelson interferometer. The original Michelson-Morley experiment, of course, did not. This is a beam splitter, okay, which is a partially silvered piece of glass. Up here we have a mirror. Half of the beam bounces off the beam splitter, goes up to the mirror, and then comes back towards the beam splitter. The other half of the beam goes this way to another mirror. And this one is movable. So it's going to go back and forth. Those two beams come back to the beam splitter, they recombine, and they go to a detector. So if I think about the two arms of this interferometer, I can consider the two lengths, L1 and L2. And if we have L1 equal to L2, then we get a certain condition. And if we have L1 equal to L2 plus a half, a wavelength, then we get a different condition. Okay? And one of these is constructive and one of them is destructive, and it depends on the reflection from the beam splitter. So if L1 is equal to L2, we get one of those conditions. If we move this mirror by a half a wavelength, we get the other condition. Constructive becomes destructive. And if we go back, then it becomes constructive again. Okay, so what is this good for? What it's good for is the following. Let's say that we don't move this mirror at all. It's just going to sit there. And I set this thing up to have constructive interference, so I have a lot of light coming to my detector. If something comes along and moves this mirror, I can detect it, right? And I can detect movement to a half the wavelength of light. So that is very sensitive. The Michelson-Morley experiment is the following. Let's build one of these things. Let's set it up such that we get constructive interference, lots of light at our detector, and now let's just monitor that 24 hours a day for an entire year. Okay? And this was an experiment done in the 1800s. And it was trying to address this question in physics of what do electromagnetic waves propagate through? When we think about waves on the ocean, they're propagating in water. If you think about waves of sound, it's propagating through air. But what about these electromagnetic waves? What are they propagating through? And there was something called the ether that everybody said these electromagnetic waves must be propagating through. And we don't know exactly what this ether is, but if there is an ether and the Earth is drifting through this ether, then it should change L2 relative to L1 as a function of time of day and time of year as we orbit the sun. And so that was the experiment that they set up. They said, let's figure out what this ether is going to do to our Michelson interferometer. And when they were all done, they discovered it did nothing to their interferometer. There was no ether. Okay? Electromagnetic waves don't have to oscillate in something. They can oscillate in pure vacuum with nothing around. And it wasn't really until Einstein came around and said, yeah, we don't need that ether. That's way too complicated. Let's just sweep that under the rug. That the results of the Michelson-Morley experiment really gained foothold, and everybody said, that's what that was. There is no ether drift. And it was built on this interferometer that was 20 feet long. It was floated on a pool of liquid mercury, okay, to try and isolate it from all these vibrations. And they did this for a full year. It's pretty remarkable. All right, there's one more experiment that is ongoing right now, which you guys should take a look at. Okay, this is one of the most famous ones, but there's another one going on right now using a Michelson interferometer and it's called LIGO. Anybody know what LIGO is trying to do? LIGO is trying to detect gravitational waves. One of Einstein's predictions was there should be gravity waves that are propagating through space. Not electromagnetic waves, not acoustic waves, something else entirely called gravity waves. And LIGO is a pair of these giant Michelson interferometers, and LIGO stands for the Laser Interferometric Gravitational Observatory. And they built one of these up in Washington and one of them in Louisiana. And these things are gigantic. The arms are like 4 kilometers long. The whole thing is in a vacuum tube. Okay, they have these giant lasers that are operating all the time. And what they're looking for is gravity waves. If a gravity wave comes along and changes L2 just slightly, they should be able to detect it. And so these things are up and built and operating right now. And you can go online and take a look at them. It's really fascinating stuff. It's fascinating because they are looking for movements of this mirror that are on the order of 10 to the minus 15 meters. That's what this detector is trying to do. And that's a little bizarre to even think about, right? I mean, an atom has a radius of about 10 to the minus 10 meters. The nucleus has a radius of about 10 to the minus 14 meters. And so now you're talking about the fraction of a nucleus, that sort of distance that you can detect.